Uh, yes, and I've been doing quantum computing for the last 3 years, and that's exactly what I'm gonna talk to you about today. This was a joint project with Lockheed Martin, and for legal reasons, I can only tell you what I did in this project, but I can assure you it's pretty interesting. So and it's scaling quantum optimization applications, meaning that we will work with QAOA. If you haven't heard of it, I'll introduce the important parts of it during the talk. And we want to scale it as much as we can, and we want to use the NISQ devices. That's basically the whole idea. Um, well, in the Algo Lab, so I'm a quantum software developer at the Algo Lab at the Institut Quantique at the University of Sherbrooke. And we are having our Algo Lab summer school on near-term quantum algorithms. So if you want to log in, register, here's the QR code. You can just Google it too, the Quantum Algo Lab Summer School. And you can join us from June 2nd to 14th. And it's going to be in Juvence, Quebec. So take a note. Okay, so just a quick introduction to what we want to do here is we have some gates, and these gates are produced by electrical pulses on the machines on superconducting quantum computers. And this takes a certain amount of time. And there are two sets of gates that we're interested. One is the swap gate, and the other one is the RCC gate. This is a parameterized gate, and it depends on a parameter theta. And what we would like is to take these electrical pulses and make them shorter by doing some optimization. So this now measured in nanoseconds. Now, the DT has to do with how the device measures its units of time, but translated to nanoseconds, it's in these numbers. So the swap gate is 1200 nanoseconds, and the RCC gate is like 800 nanoseconds. And we want to reduce this. And the idea is that these two gates appear a lot in this QAOA algorithm. This algorithm, it comes in the form of layers, and it's a hybrid algorithm, meaning that it runs, some parts of it run on the quantum device and other parts run on a classical device, and you need this classical quantum loop to train it. So this is the part that runs on the classical device. And these two gates, the RCC and the swap gates, these are repeated a lot of times inside the inner layers of QAOA. And the part that we want to scale is the depth of QAOA, because there is a theorem that says that the QAOA circuit can express the optimal solution to the combinatorial optimization problem when the length of these layers goes to infinity. So we cannot do this like for a high number, but what we want to do is we want to be able to do these gates in a shorter amount of time. Well, inside the QAOA circuit, for instance, this is one small example for 3 qubits. And we start with the superpositions, and there are two pieces of the QAOA circuit that are very important. One is called the problem Hamiltonian. It comes from the problem Hamiltonian, and it depends on the problem graph. So since we're doing combinatorial optimization, this problem comes encoded in the form of a graph. And sometimes, and there's a mixer Hamiltonian that is important for other things, like to prove this theorem that you need. And these swap gates, they appear because the physical device, like you may use the physical qubits on the device, but they may not be connected as those on your problem graph. For instance, if your physical device is like this, there's no connection between 0 and 2, which means that you have to swap either qubit 0 and 1 or qubit 1 and 2, so that 0 and 2 are close to each other for you to apply the next gate that involves these 2 qubits. And then you need to take back these two to its own place. So this makes it a little bit more complicated. You have more complicated graphs, and actually on the quantum systems, we have the connections are not that complex, so you really need to do a lot of swaps to get arbitrary graphs. And in these cases, it's like this. Now for 65 qubits, now there's no more 65 qubits devices, but for 127 is like this. So, and you will have like to deform this graph using swap gates, and you will need a lot. So you need a lot of swap gates if you really want to make QAUA useful. Okay, now in the physical device, we have a way to look at the Hamiltonian of this object. And in terms of quantum mechanics, what that means is that if we understand the Hamiltonian, we can control this quantum system, and we know the outputs that it will give us, and so on and so forth. Now, what you can see here on the screen is two qubits connected by a capacitor, and each one has its own uh, how do you call it, like a pulse that you send to it to change its quantum state. Now, each part of this diagram has its own Hamiltonian. This part here, I will call it the part of the qubit 1, and its Hamiltonian comes in the form of HQ1. Same thing for the other part. This is the second qubit, but we also have the Hamiltonians for each one of the pulses. The pulse that is being sent to Q1 and the pulse that is sent to Q2. And there's also one part here in the Hamiltonian that represents the connection between these two qubits, between these two systems. And this is controlled by a parameter J. Now, why do we care about this? Because we would like to do pulse optimization. Now, pulse optimization means you're gonna take a pulse and you're gonna reshape it so that it gives you the right output that you want. And since you want the way that you measure if you have the output that you want is by using the Hamiltonian of the system. So in Open Pulse from Qiskit, this allows you to play around with pulses and send custom pulses. And so the equations look kind of like this. Now I could tell you how each one of these equations relate and how you work around the optimization, but it's pretty simple. Like you just need to follow the chain rule when you do derivatives, and it tells you how to follow the gradient in this case. It's actually gradient ascent because the cost function it has a minus sign somewhere. Now there's some limitations, and is that not all the coefficients of the Hamiltonian of the physical device are known. So for instance, in this expression, for HQ1 and HQ2, each one has the two factors that are the Josephson energy and for each one of the qubits, but also this J, which is the coupling between the two qubits. This is not known, and you have to do it by experiments. So some of these values, they can be determined by these experiments. Now, by sending pulses with different shapes and different sizes, you can get curves, then you do a curve fitting, and that gives you one of the parameters. And then you can do this a couple of times to get a pretty good approximation of the actual Hamiltonian of the system. And once you do that, you need to do the optimization, and this is called GRAPE. And it's the letters for gradient ascent pulse optimization, pulse engineering. And what you do is, given the Hamiltonian of the system, which we already have because we did all these experiments. Now, of course, this Hamiltonian will be simulated, so it will still be a simulation of the approximation of the actual Hamiltonian. Now, you initialize a random pulse, and then you make discretizations on this pulse. And this is one of the parameters that you have to tune when you do these optimizations. And what you do is you compute the gradient with respect to the height of each one of these discretizations on the pulse. And then you follow the gradient, and that gives you a shaping of the pulse during the optimization. Yes, and we want to minimize leakage. This means that the information is going, since these are transmon qubits, you may have leakage to higher energy levels. You want to minimize that. You want to keep on the first two energy levels of your qubit, but also you want to maximize gate fidelity, meaning that you did the actual computation that you wanted to do in the quantum system. Okay, now for the case of the swap gate, we did this. Now currently, if you do a swap gate, this means you're applying 3 CNOTs, and this gives you 1200 nanoseconds. Now, after running a couple of optimizations and getting the optimal one of those, we found one with 320 nanoseconds. Now this pulse makes the same operation, and it minimizes leakage and it maximizes gate fidelity. Okay, and so this means we've seen an improvement of 73% on the length of the swap gate. Now this other gate, this RCC gate, this is a parameterized gate. So for a given parameter, what we have is that right now you need, in terms of nanoseconds, this is 800 nanoseconds, and we found another one with 320 nanoseconds that does the same operation, and this means we have an improvement of 60%. And what we did is since this parameterized gate needs to produce a pulse for every theta, and this theta will be optimized during the QAOA optimization. That means that for any theta, we should be able to produce a pulse. And that looks like a task for a neural network, for an AI. And that's what we did. So basically, we ran a lot of samples for this optimization on grade, and we created a data set of 100,000 angles between 0 and 2 pi. Then we produced for each one of the angles, we produced a pulse schedule that corresponds to the gate on this specific angle. So that's why we use a lot of GPU hours, because we did a lot of trainings. Yes, so in this case, what you see is, here you see 8 crests, and that's because each qubit, the way we engineer the pulses, each qubit receives 2 pulses, and each pulse is complex. So that's why you see 8 here, because each qubit receives 2 pulses, and each one has its real and imaginary part. So the first crest is the real part of the first pulse, second part is the imaginary part of the first pulse, and so on and so forth. And here in red, this is the ground truth, the pulse that was optimized, that we know that gives us the operation we want. And the blue one is the predicted by the trained neural network. Now, the way we partition the data here on the left gives us some big errors between the crests. So we started doing it we gave it other approaches. So we optimized like crest by crest, but this we have to optimize a neural network per crest, but still it can be done. And the approximation is better in this case. And now this, I think this is a video. Yeah, okay, so what we did is, we did a PCA on the data set of pulses, and then we learned the principal components only. So, and what you see here is the learning at different epochs, how the prediction evolves. It should stabilize somewhere. Yes. So as you can see, it's not better, and it stays like this, like for the next 100 epochs, I guess. But that's the idea. The idea was to use neural networks to help us build these pulses. And what we said was okay, let's try this on one pulse, like one complex pulse, and then look at the measurement outcomes of the differences between the prediction of the neural network and the pulse that we already optimized. And what happened was it looks good. So to measure like the zero state, when you send, what we did is, the experimental setup is, you have the zero state, you send the pulse from the grape optimization, and then you measure the probabilities of getting 0 or 1. And we got these 2 values. But for the pulse on the neural network, you can see that the difference is very small, and that gives us like 10% difference. But this is just for one pulse on one of the qubits on this big circuit that we wanted to approximate. So the outcome of all of this is that you should do better optimizations. After finishing this project, we started working with the loss function. Now the loss function of the neural network, and this also comes from a paper. I don't remember the authors, but someone already did this. is putting the Hamiltonian directly in the loss function of the neural network, and that helps learn the pulses better. So that's it. Thank you very much.
All right, Marco, thanks so much. That was really interesting. I have to say, I'm a sucker for a good acronym. GRAPE is awesome. One of the first packages that I ever was a part of in grad school was called Cucumber. It was basically just like the acronym is horrible. It's a huge reach, but it was a package for restricted Boltzmann machines for like classical machine learning. Anyway, I'm a sucker for a good acronym, so that was good. Okay, so we have a couple questions from the chat. I think this had to do with an earlier slide in your presentation. This one's from Quantum Catalina. Would this work on any quantum device or just a specific one? So I think this is just in relation to something that you showed in your first few slides. Maybe we can go back to that.
Which one?
Yeah. Okay. Maybe we can come back to this question. Actually, if Quantum Catalina wants to clarify there, we can continue.
Okay.
I think it's this, but yeah, let's just wait for Catalina to clarify. Another question from.
I can just.
Sorry. Go ahead.
Oh yeah. So this is for any superconducting quantum computer, and in particular, IBM does it like this. Right. And this circuit, this is called circuit quantum electrodynamics, and everyone that is doing superconducting qubits, it's doing something like this. So the mathematics of this that I showed you, how to get the Hamiltonian, how to produce the experiments that give you the values on the Hamiltonian, that you can reproduce it on any machine that is superconducting, that uses superconducting qubits. And also the QAUA algorithm, this is gate-based, so that's also another thing that to keep in mind. But in principle, yes, this whole pipeline can be reproduced in any superconducting machine.
Yeah, and Catalina actually clarified in the chat, so that answered the question, so thank you. Another question from Broken Symmetries. How do you find the sweet spot between maximizing fidelity and minimizing leakage?
You don't. You compromise from the beginning. So basically what we did is we constructed a loss function, a cost function that has 1/2 for the minimization of the leakage and 1/2 for the how do you say, which one was it? The one is minimization of the leakage and the other one is maximization of gate fidelity.
Yeah.
Yes. So you put it 1/2 and 1/2, and then it reaches 0. So that means that both are 0.
I see. Okay. Another question from Andresulid. In general, pulse scaling is done for 2 qubit gates. The idea is to try to reduce the rotation angle generating the same effect.
Say again.
Yeah, I'll try and read that again. In general, pulse scaling is done for 2 qubit gates. Is the idea trying to reduce the rotation angle generating the same effect?
Not the rotation angle, the length of the pulse.
The length of the pulse.
Yes, okay. Which is different. They may be related, but not in general.
Okay. All right, so that's the time that we have. But if there are any more questions for Marco, Marco, you'll be on the Discord shortly after your talk. So thank you for that. Everybody, let's give one more thank you to Marco, and thanks again, Marco, for your talk. And cheers. Have a great rest of your day.
Thank you.